So now that we've talked a bit about parametric equations and what parametric equations are, what we need to do now is we need to look at the calculus on parametric equations. We need to look at how do we now translate the work that we've done in rectangular coordinates and the rectangular system into the parametric system, or into the parametric equation system. So where we're going to start then is we're going to start out with the derivatives of parametric equations. Okay? And so basically, what we're going to look at here in order to do that, we're going to say, okay, let's say, for example, I want to know what dy dx is. Okay? And I have x of t and y of t. Okay? So those are my values here. Okay? Now, what I'm going to see, okay, or what we've seen previously before, is that y of t is going to equal f of x of t, right? Where f of x is the rectangular function, okay? Is that rectangular function. So basically what this is, right, is this is showing us if I plug in whatever my parametrization of x of t is into my function f, I'm going to get back y of t. So now what we're going to do is we're going to use the product rule. Okay? And so when we use the product rule, y prime of t is going to equal f prime of x of t times x prime of t. And since f prime of x of t, okay, equals dy dx, what we can do is we can then just substitute. And so we'll get y prime of t is going to equal dy dx times x prime of t. And so dy dx, my derivative, the one that I'm looking for here, is going to equal simply x prime of t over y prime of t. And that's our derivative. So if x of t and y of t are parametric equations, then dy dx is going to end up being x prime of t over y prime of t. Let's take a look at this example. So now I have x of t equals t squared minus 3, y of t is going to be 2t minus 1, and we're going to go from t greater than or equal to negative 3 and less than or equal to 4. Okay? So what we want to do is we want to actually go out and figure out what the derivative is, right? So what is dy dx? So that's what we're looking to find. So what we'll do is we'll take x prime of t, and that's going to equal 2t, right? So we'll basically take the derivative of x with respect to t, and then we'll find y prime of t, which is just equal to 2. So dy dx is going to equal y prime of t over x prime of t, which simply equals 2t over 2, which equals t. And that's the derivative of this parametric equation. Now let's say that what we want to do is we want to locate any critical points. So in that case, that's where dy dx equals 0. And so this is where t is going to end up equaling 0. Notice that t equals 0 is in the interval, so we will have a critical point within that region. So there it is, t equals 0 is our critical point. Let's take a look at this question. Let's say we have x of t equals 2t plus 1, and y of t equals t cubed minus 3t plus 4. And we're going to be on the interval of t from negative 2 and 5. So dy dx is going to equal x prime of t, or excuse me, y prime of t over x prime of t, which is, so x prime of t is just going to end up being 2, and y prime of t is going to end up being, excuse me, x prime of t is going to be 2 on the bottom, and y prime of t is simply going to be 3t squared minus 3. And so consequently, we can just rewrite this as 3 halves t squared minus 3 halves. If we wanted to look for critical points, what we could do is we could then just set this equal to 0. So we'll say, okay, where is 3 halves t squared minus 3 halves equal to 0? Well, we'll take 3 halves out, And we'll end up with t squared minus 1 equals 0. And so this will then give me that 3/2 times t minus 1 times t plus 1 is going to equal 0. So t will equal 1 or negative 1. We look at our interval, and our interval contains both negative 1 and 1. So t equals 1 or negative 1 are the critical points. Now let's take a look at a question that's affiliated with finding the derivative. Let's find the tangent line to the curve that's defined by x of t equals t squared minus 4t, y of t equals 2t cubed minus 6t, and t greater than or equal to negative 2 and less than or equal to 10. And we want to find it when t equals 5. Now notice this is a bit different. It's not when x equals something. It's going to be when our particular time t equals something. Now, we need to find dy dx because dy dx is going to be the slope of the tangent line. Now, what I'll do first is I'm not actually going to find dy dx. I'm going to find x prime of t, which is going to equal 2t minus 4. And I'll find y prime of t, which equals 6t squared minus 6. And since I'm looking for the derivative at a particular time when t equals 5, rather than going through and simplifying, I'm going to find x prime of 5, which equals 2 times 5 minus 4, which is 6. And I'll find y prime of 5, which equals 6 times 5 squared minus 6, which is, that's 150 minus 6, so that's 144. So dy dx, when t equals 5, is going to equal 144 over 6, which ends up equaling 24. So that's the slope of my tangent line. Now, I just plug in the values for my slope of my tangent line, but oh wait, I have t's, but what I don't have is I don't actually have x and y's. So I need to find what x of 5 is, right? Notice, not the derivative. I just need to know what the x value is at t equals 5. So that's not the derivative. I find x of 5, and that'll be 5 squared minus 4 times 5, which equals 5. And then I'll find y of 5, same thing, not the derivative, okay, which is 2 times 5 cubed minus 6 times 5. And so this ends up being 250 minus 30, which equals 220. So what that means is that the equation for my tangent line is going to be y minus 220 equals 24 times x minus 5. Okay? If we simplify this, this will give me y minus 220 equals 24x minus 120. And so that'll end up giving me then, when I add 220 to both sides, this will give me y equals 24x plus 100. So notice, in this case, all I really want to do is I want to say, okay, well, I know dy dx, my derivative, is going to be y prime of t over x prime of t. So what I'll do is, rather than going out and doing any kind of simplification or algebra, I'll find literally y prime of 5 and x prime of 5 and just divide those two numbers. Okay? And that'll give me the slope of the tangent line. Then, what I want to do is I want to go out and find what are the values for x and y at that point t, or at t equals 5. Well, that means that I've got to go back up to my original parametric equation, plug in the 5's, okay, to find those values of x at those points. Now let's find the second order derivatives. So what we're looking for is we're going to be looking for d squared y dx squared. And what you want to notice about this is that this is actually d dx of dy dx. So basically we're just doing the same process or operation that we were doing on y. We're going to do it again to dy dx. How we're going to do that is just by utilizing some kind of, basically an algebraic trick. What we're going to see is we're going to notice, okay, we'll note that if I take dy dx, that's equal to y prime of t over x prime of t. And that's actually equal to d dt with respect to y, okay, over x prime of t. Okay? So what we'll do for d squared y dx squared is this is just going to be d dx of dy dx. And just like we replaced y here, we're going to do the same thing in dy dx inside of this other one, the parametric derivative. So this is now going to be d dt of dy dx divided by x prime of t. And that's going to be the derivative. So we rewrite this, and that's d squared y dx squared. The second derivative is going to equal d dt of dy dx over x prime of t. So let's find the second derivative now. And let's say we have this parametrization. We have x of t equals t squared minus 3, y of t equals 2t minus 1, and we'll go from t is greater than or equal to negative 3 and less than or equal to 4. So first what we're going to do is we're going to find dy dx. Okay? So dy dx is going to end up equaling y prime of t over x prime of t. And that ends up being 2 over 2t, which is simply 1 over t. So that's dy dx. Now remember that d squared y dx squared is going to end up equaling d dt of dy dx divided by x prime of t. And so we pretty much have this. We know that we have d dt of dy dx. So the derivative with respect to t of 1 over t is going to end up being negative 1 over t squared. And then x prime of t, once again, is just 2t. And so this ends up equaling negative 1 over 2t cubed. What exactly you are going to be doing to find the second derivative? Well, what we did first is we first found out what dy dx was, okay, by utilizing our formula, y prime of t over x prime of t. And then I replugged that back into the derivative. So I took d dt of that dy dx, and then I divided that again by x prime of t. And that gave me my second derivative. So let's say, for example, now I want to find d squared y dx squared for this parametrization. X of t equals 2t squared minus 4t, y of t equals 2t cubed minus 6t, and t is greater than or equal to negative 2 and less than or equal to 3. So what we'll do is we're going to first find dy dx. Okay? So dy dx is going to equal, so that's y of t, so that's going to end up being 6t squared minus 6 divided by, and then x of t, which is t squared minus 4t, so it's 2t minus 4. Okay? Do a little simplification here. We'll pull out the 6. We get 6 times t squared minus 1, divided by, and this will then be 2 times t minus 2. Well, what we'll notice is that that's basically going to just allow us to rewrite this as 3 times t squared minus 1 over t minus 2. But we can't really actually take this any lower than that. So what we're going to do now is we're going to find d dt of dy dx. Okay? d dt of dy dx. And so we'll utilize the product rule in order to do that. So that's going to end up being, we'll multiply that by t minus 2. And then we'll subtract 3 times 1, because that's the derivative of t minus 2, times t squared minus 1. All divided by t minus 2. This will then give us 3 times, and this will be t squared minus 2 minus t squared plus 1. All divided by t minus 2. And that will then equal 3 times negative 1, right? Because these two cancel. So we end up with negative 2 plus 1. So this is 3 times negative 1, so it'll be negative 3 over t minus 2. Awesome. So that's actually the top part. So now remember that d squared y dx squared is going to equal d dt of dy dx all over x prime of t. So this ends up giving me negative 3 over t minus 2, because that's what that is, divided by, and x prime of t is 2t minus 4. Well, this is then going to equal negative 3 divided by 2 times t minus 2 squared. When we pull out the t minus 2 out of here, because this is going to end up being 2 times t minus 2. Right? That's the simplification of this value right here. And there we go. And that is our second derivative. Now, from the second derivative, we can find things like points of inflection. Right? Okay, inflection points, we can find concavity. All right, we can find concavity for parametric curves. So for what values of t are we going to have something that's concave down or concave up? Right? And all we've got to do is we've got to figure out what the value of t is that makes it negative or makes the second derivative positive. All right? So we can do a lot of things with that second derivative. So now let's talk about integration using some parametric equations. So let's say, for example, what we're going to do, we're going to basically be finding the area underneath the curve of a parametric equation. So let's take a base case scenario. Let's say, for example, this is our parametric equation. Okay? And what we want to notice here is that I can imagine breaking this up into rectangles. And for our purposes, we'll just use right-hand rectangles. All right? Something along these lines, right? And we'll make each one of the intervals be exactly the same, just like we have in previous incarnations. So, like for example, this would be just simply it's a delta x, but we'll call it x. And since we have a parametrization, this is going to be x of t naught. So the very first t time, then we'll have x of t1, so on and so on and so forth until we get to x of tn. Now, the heights of each one of these rectangles, right? This is simply actually really going to be just y of t, okay? So, or y of t naught. This is going to be y of t1, right? Because they're going to just kind of correspond with the same time t, right, that we get with each one of the x's. Now, what we can do, or what we're going to do, is we're actually going to say, well, actually, what I want to do is I want to line it up with x of t naught. So I'm going to make this y of x of t naught. Okay? And this is y of x of t1. And so on and so on and so forth for each one of our y's. And so that ends up being the height of each one of these rectangles. Okay? And so basically, those are the values that we're going to end up getting in order to like kind of find the overall height of our rectangles. Okay? So what we'll do is the area of any one of these rectangles, or AI of each one of these rectangles, is going to end up equaling y of x of, and let's just use the midpoint, okay? Or right-hand side, it doesn't actually really matter, okay? We'll call it ti bar, times, and this will be x of ti1, or ti, minus x of ti minus 1. All right, so that's pretty standard in terms of finding the area of a particular rectangle. Now, the area of the entire region, AN, is then going to end up equaling the sum of these, I equals 1 up to n, of y of x of, in this case, ti dash, times x of ti minus x of ti minus 1. All right. And now what we're going to do now, okay, so there's our AN. What we're going to do is we're actually going to multiply. We're going to need to multiply and divide by, or let's just go in and we're just going to now multiply by ti minus 1 divided by ti minus 1. All right. And what that's going to allow us to do is that's going to allow us to put everything in terms of dt. So this is now AN is going to equal the sum, I equals 1 up to n, of y of x of ti bar times x of ti minus x of ti minus 1, take that all divided by ti minus 1 times ti minus 1. What we'll do then is we're just going to switch out for delta x, okay? So this is going to end up being, or excuse me, for delta t. So this an is now equal to the sum I equals 1 up to n of y of x of t bar I times, and so we've got this, part of me is just wants to call it delta x of t, right? But we can't really do that. We're just going to write it as x of ti minus x of ti minus 1 all over delta t times delta t. Now here's the thing. My t's are all the same size, right? And that's one of the reasons why we had to do this, is because it technically is not the case that all of our x's are the same size. They may not be actually all the same interval length, right? That's kind of the idea we're playing with, but they may not be. But we do know that our delta t's are, right? Because those are going to be the actual intervals of our dependent variable. So what I'm going to do now is I'm going to take the limit as n approaches infinity, right? Just like I've done with every other integral. And this is going to be of y of x of ti star times this x of ti minus x of ti minus 1. And those are just the parametrization of x evaluated at each one of these values, divided by delta t times delta t. Okay? And so, here's the deal. So what's happened now is we now, because we've taken this limit as it goes to infinity, we know that this is going to end up becoming dt. And this actually right here is going to end up becoming dx dt, because ti to ti minus 1, they're going to end up getting very, very small. That difference is going to get very small. Okay, so this is going to end up becoming basically, or not dx dt, it's going to be x prime of t. All right, and, well, which is dx dt. And this thing right here, because each value x of ti, these values of t, we're going to get, basically they're going to be evaluated at individual points, right? Individual points, that's just going to end up being y of t. So this is going to end up being the integral, okay, from t naught to call this tn, or a to b, whatever our values are, t naught to tn, of y of t times x prime of t dt. And that's the integral. So that is how we find the area under a curve for a parametric equation. The integral from t naught to tn, or we'll call it t1 to t2, right? The endpoints of our interval of y of t times x prime of t dt. So now what we want to do is we want to find the arc length of a parametric curve. And this is the next step in terms of creating a calculus for parametric equations. So we know that we'll end up having the integral. And this integral, let's say, for example, it's going to go from x1 to x2. Okay? And its arc length, so s, is going to equal, from x1 to x2, 1 plus dy dx squared dx. And that's actually the integral for our arc length. Now, what I'm going to do is I'm actually going to transform this. I'm going to get my arc length, and I'm going to transform it into terms of parametric equations. Well, x1, okay, is actually going to end up being x1 of, say, call it t1. So the first part of our interval is going to be at t1. So this is our lower bounds on our integral. And x2 is actually x2 of t2, all right? And so t2 will end up being our upper bounds. Now remember that dy dx is going to end up being y prime of t over x prime of t. So s is going to end up equaling the integral. We'll change our bounds from t1 to t2. It'll be the square root now of 1 plus y prime of t over x prime of t squared, dx. Now, I want to do something with dx because I'm not actually going to integrate with respect to x. I'm going to integrate with respect to t. So recall or remember that dx dt equals x prime of t. So that means that dx is going to end up equaling x prime of t dt. And there we are. Okay, so that's going to be their substitution for dx. So s is now going to equal the integral from t1 to t2 of the square root of 1 plus y prime of t over x prime of t squared times x prime of t dt. Now that we've got our substitutions done, all we really need to do is we just need to go in here and we just need to do some algebra. So this is going to be the integral from t1 to t2. You'll see it written as a to b. And so this will be the square root now. And if I'm going to, my common denominator is going to be x prime of t squared. So this is going to be x prime of t squared. Okay, x prime of t squared plus y prime of t squared all over x prime of t squared times x prime of t dt. Now this is then going to equal the integral from our t1 to t2, the square root, and what I'm going to do actually is I'm going to pull out 1 over x prime of t. So 1 over x prime of t, because we have it squared, the bottom part there. And this then will be times, and now we can't do the same thing to the top because it's over over addition. So this is going to be x prime of t squared plus y prime of t squared times now x prime of t dt. Well, the x prime of t is going to cancel out, and I'm going to rewrite x prime of t and y prime of t as dx dt and dy dt in Leibniz notation. So this is now going to equal t1 to t2, okay, the square root of, and this will be dx dt squared plus dy dt squared dt. And that is the integral for our arc length. So our arc length is going to be the integral from t1 to t2 of dx dt squared plus dy dt squared dt. And again, what we're going to be doing is we're going to be integrating with respect to t. We can go through, we can do this via, utilizing the definition for the integral, but I think that probably this is the more, for me at least, this is the more intuitive way of going about things. Okay? So let's do some examples. Let's take the example. We'll have x of t equal 3 cosine t. We'll have y of t equal 3 sine t. And we'll go from 0 less than or equal to t less than or equal to pi. Now, if you kind of think about what this is, remember some of our discussion about parametric equations, this is going to end up being a circle with radius of 3. Okay? And we are only looking from 0 to pi, so we're going to be looking at the top half of this particular circle. And there is that top half, radius 3. Okay? So we could go out and we could, if we wanted to, we could go and find what that arc length is just by taking its circumference. But we're not going to do that because we've got to actually do this demonstration. So we're going to have the integral of 0 to pi. And then this will be the square root. We'll take the derivative of x prime. So this is going to end up being negative 3 sine t squared plus the derivative of y prime, which will end up giving me 3 cosine t squared, and then just dt. This then equals the integral from 0 to pi, okay, of the square root of 9 times sine squared t plus cosine squared t dt. And so that's the integral from 0 to pi of, we'll pull out that's going to be 3. This is going to end up being 1. So this is going to end up just being 3 dt. And then we'll evaluate, right? This is going to end up being 3t, evaluated from 0 to pi. Okay? And so that ends up being 3 pi. Weird, right? Exactly what we thought it was going to be. So that's your arc length equation. Basically, again, we're going to be utilizing the derivatives right? The derivatives with respect to x, the derivatives with respect to y, okay? And then it's just a matter of going through and utilizing our integration techniques. So what about the surface area generated by a parametric curve? Well, it's going to look a lot similar to what we have been doing. So imagine we've got a curve, okay, curve in space. Here's our parametric curve, all right? It's got a parametrization. What we do is we revolve it around an axis of some sort, okay? And what we get, right, is we got this revolution somehow. This is going to be from the value t equals a up to t equals b. And so we already know, if we weren't parametrized, if we had it in terms of x and y, that s is going to equal 2 pi times the integral from a to b of f of x times the square root of 1 plus f prime of x squared dx. Well, here's what we're going to need to get, okay? We could go into and talk quite a bit about like using that definition of the integral, talking about accumulation and accumulating portions of parametric curves. But really, this is just analogous to what we did with the arc length. Okay, notice that this right here, that's the arc length. The square root of 1 plus f prime of x squared, or actually that's the derivative of the arc length. And so we actually already know what that is. Okay, the square root of 1 plus f prime of x squared dx is going to be equal to, or is analogous to, dx dt squared plus dy dt squared dt. And then it just turns out that this f of x, that's just values of y along the curve, along the parametric curve, right? Based upon t equals a to t, from t equals a to t equals b. So my surface area, so for the parametric curve, my surface area is actually a pretty simple substitution. Okay, we can get into, like I said, we could get into a lot more explanation, but we don't really need to. The surface area is going to be a to b, right? T equals a to t equals b, not this one here, which is kind of like x of a to x of b, really. So s equals a to b, and it'll be f of x is going to end up being y of t, and then this part right here is that surface area, so it's going to be times the square root of dx dt squared plus dy dt squared dt. And that is our formula for the surface area. And there you go. Call this surface area. S was also called arc length, which we call it surface area. So let's take a look at an example. Let's say, for example, that x of t is equal to 3t squared, that y of t is equal to 2t cubed, and we are going to be finding that the area of the surface revolution from t equals t greater than or equal to 1, less than or equal to 3. Okay? So I will set this up. I'm going to first find that x prime of t is going to equal 6t, and y prime of t is going to equal 6t squared. So my integral is going to go from 0, or it's not 0, it's going to go from 1 to 3, and it'll be y of t, so it'll be 2t cubed times the square root of 6t squared plus 6t squared squared dt. So this ends up equaling now the integral from 1 to 3 of 2t cubed, right, times the square root, and this will be 36, okay, 36t squared times 1 plus t squared dt. So this will then end up equaling the integral from 1 to 3, 2t cubed, times now 6t times the square root of 1 plus t squared dt. And that'll then be the integral from 1 to 3 of 12 t to the 4th times the square root of 1 plus t squared dt. And I'll let you go out and do the integral for on your own on that one. Just a quick hint. If we let t equal tangent of theta, okay, then that actually should allow us to go out and solve this using a trigonometric integral. Your hint. All right. So that's how that works. Once again, it's just a matter of setting it up, being able to find those derivatives with respect to t, and completing the setup. So this completes our section on doing calculus on parametric equations. There are corollaries to doing calculus utilizing any of the calculus that we've learned before inside of parametric equations. There are just some slight variations, slight changes that are needed, but they're important. So you really need to make sure that you go and you study these, and that you do some practice with them, because it'll make things a lot easier, okay? And it'll also, kind of help you to really understand what we do when we do parametric equations.